Okay, this is a review for second exam covering Chapter 3 in the 6th edition of the textbook, Chapter 4 in the 5th edition if you still have that one. Anyway, this question comes from the first section of the chapter. Express the quadratic in standard form. The directions that aren't written here is by completing the square. That's the intention here. Same thing on question 2, by completing the square. So the way it was introduced, at least the way I introduced it in class, if you were there, is to take this constant, move it to the other side. So I'm going to subtract 12. F of x minus 12 equals x squared minus 8x. Now there used to be a 12 there. We've got to fill in that blank spot with a perfect square. And if you're good at remembering formulas, the formula is b over 2 squared, where b is that. So if you can remember a formula, that's what you want to do. Rather than memorizing formulas, this number here needs to be a perfect square. So you look at the middle number. 8 is 4 plus 4, so the number that needs to go here is 4 times 4. So you're going to put a plus 16 here. You've got to keep the equation balanced, so if you add a 16 on one side, you've got to add a 16 on the other side. That makes f of x plus 4 is equal to x squared minus 8x plus 16. Now the reason for the 16, it turns this into what's called a perfect square trinomial. This x squared minus 8x plus 16 can be factored into x minus 4 times x minus 4. I'm going to factor this into x minus 4 squared. And the last step is to move the 4 back over. So the final answer is f of x equals quantity x minus 4 squared minus 4. Okay, question 2, a similar problem. There are a few differences. It starts the same way. I'm going to move this 14 to the other side. We have f of x minus 14. The difference in this is there's a leading coefficient. If there's a leading coefficient, even including just a negative 1, if there's any leading coefficient other than 1, you want to factor that out. Now you're not going to factor it out of the 14 because it's not there anymore. So I'm going to factor out the 2. That's going to leave me x squared plus 6x. I'm going to close the parenthesis way out here because this is where you're going to add that number that completes the square. 6 is 3 plus 3. So 3 times 3 is going to give us a plus 9. Okay. Now we've got to balance out the equation again. It really isn't a 9 that has been added to the right side of this equation, because if you redistribute the 2 back into this parenthesis, 2 times 9 is really an 18. So we've added 18 to the right side of the equation, so you've got to add 18 over here, and you get f of x plus 4 equals 2. Now x squared plus 6x plus 9 factors into x plus 3 times x plus 3, and that's x plus 3 squared. And again, the last step is to subtract a 4. So the final answer is f of x equals 2 quantity x plus 3 squared minus 4. Now we're supposed to graph the function. That's one of the reasons, not the only reason, that's one of the reasons for this whole process is graphing a quadratic is much easier to do if the quadratic function is written in standard form, or vertex form as it's often called, because you can use transformation graphing. This plus 3 moves the graph to the left 3 units, minus 4 moves the graph down 4 units. The vertex is going to be at negative 3 comma negative 4. Okay. And then this parabola is facing up because it's a positive leading coefficient. The 2 is just going to compress or stretch, I guess, the graph vertically. So it's going to be a little bit of a skinnier parabola. We need to find out another point on the parabola to make the shape a little more exact. So I'm going to plug in a negative 2 for x to see what the y value is for negative 2. So if I plug a negative 2 in, that x right there, negative 2 plus 3 is 1. 1 squared is 1. 1 times 2 is 2. 2 minus 4 is negative 2. So negative 2 comma negative 2 is another point on the graph. And then using symmetry, the line of symmetry goes right through the vertex. Using symmetry, that point gets reflected. So the parabola, something like that. Domain and range in interval notation, the domain of any quadratic function, the domain of any polynomial function for that matter, the domain is all real numbers, negative infinity to positive infinity. That's the domain. The range, if you take a look at the lowest point here, the vertex, that correlates to negative 4 on the y-axis. So negative 4 is the smallest y value. The largest y value would be approaching positive infinity. And state the intervals for which the function is increasing and decreasing. This part of the function right here, the one I'm highlighting in blue, this is a piece of the function that's decreasing. As you're moving on the graph from left to right, the y values are getting smaller, so that would be a decreasing interval. This one that I'm highlighting in red, that's an increasing interval. And if you don't happen to recall from the first unit, you only state the x values on which this is occurring. So I'm going to do the increasing first, the one in red. It starts to increase right here at an x value of 3. And then with all of these x values greater than negative 3, the graph is increasing. So it's increasing from an interval of negative 3 to infinity. Now the decreasing, it's decreasing on all of these values up until negative 3. So all of these x values up until negative 3, the graph is decreasing. So it's decreasing on the open interval negative infinity to negative 3. Okay, sketching graphs of polynomial functions, that's from section 3.2 of the 6th edition. So we need to find the zeros. We need to find the y-intercept. We need to know the end behavior. So the zeros of the polynomial are found from factored form. So our first task is to factor the polynomial to find the zeros. So this one can be factored by grouping. From the first group, you can factor out an x squared. That leaves x minus 1. The second group here doesn't look like it has any common factors, so you have to factor out a 1, and in this case, a negative 1, because there's a negative sign right there. So if you factor out a minus 1, you know what? I goofed this up. Let's back this up. If you factor out an x squared from this, that's going to leave you x minus 2. There we go. And from this, I apologize for that, and from this, if you factor out a minus 1, that's going to leave you with x minus 2. You change this to a minus 2 because a negative 1 factored out of a positive 2 leaves a minus 2. So these both have a factor of x minus 2 that can be factored out. If you factor out the x minus 2 and put that as a common factor in front of a parenthesis, then you're left with x squared minus 1. Now this is difference of squares. So it's going to be x minus 2 times x plus 1 times x minus 1. So the zeros are x equals 2, x equals negative 1, and x equals 1. Remember, zeros are the same as x-intercepts. That's why we are placing so much emphasis on finding them. So those are the zeros. Now the y-intercept is more easily found from not factored form, but from the general form up here. If you remember to find the y-intercept that all the x's equals 0. So if all these x's equals 0, you're left with a 2. So the y-intercept is a point 0, 2 up here. Now the end behavior has to do with the degree of the polynomial. That's also more easily found from this general form of the polynomial here. The degree is a degree 3. So the end behavior, I'm just going to make a quick sketch here of the end behavior would look something like this, where the left side is going down, the right side is going up. Okay? So the left side is going down, the right side is going up. Now, it's not always left side down, right side up. If there had been a minus sign in front of the polynomial, it would have been switched. The left side would be going up, the right side would be going down. But what we got to figure out is what's happening to connect these. And that has to do with the multiplicity of the zeros, because if you recall, zeros, x-intercepts, the graph doesn't always cross through, sometimes it bounces. That has to do with how often the zeros are occurring. All of these zeros have a multiplicity of 1. 1's an odd number. Odd multiplicities cross through the x-axis. So it's going to cross through to the y-intercept, cross through, it has to turn back up, crosses through there. It's a rough sketch of the graph of that polynomial. Okay. Question 4 has already been factored for us, which is nice, so all we have to do is state the zeros, we don't have to factor. So from this fact right here, we get a 0 of x equals positive 1/2. From this 0 we get, or from that factor rather, we get a 0 of x equals negative 1, but that one has a multiplicity of 2 because the factor appears twice. What that means is at this x-intercept, the graph is going to bounce at negative 1, it's not going to cross through negative 1. The other 0 is x equals negative 3. Now I'm going to place those on x equals 1/2, x equals negative 1, and x equals negative 3. Now the y-intercept, unfortunately we don't have the general form, we have the factored form, so we have to let all the x's equal 0. If this x equals 0, 2 times 0 is 0, minus 1, that's negative 1. 0 plus 1 is 1, 1 squared is 1. 0 plus 3 is 3, so negative 1 times 1 times 3 is negative 3. Now we have to consider, so the y-intercept is 0, negative 3. Now we need to consider the end behavior. The end behavior again is determined by the degree. It's a little bit harder to tell the degree when it's in factored form like this, but if you consider the zeros or how many factors there are, there's 1, 2, 3, 4. There's 4 factors, which means this is a degree 4. So a degree 4 polynomial's graph looks like a degree 2, where the end behavior is up on the left side, up on the right side, or down on the left side, down on the right side if there had been a minus in front. So up on the left, up on the right. Now as the graph approaches that x-intercept, it only has a multiplicity of 1, so it crosses through. And we know at some point it has to turn back up and head here, but exactly where it turns up, to find it exactly, you either have to have calculus or a calculator. We don't have either yet, so we're just going to estimate, and I'm going to plug in negative 2 as the next value to see where the graph is at negative 2. 2 times negative 2 is negative 4, minus 1 is negative 5. Negative 2 plus 1 is negative 1, but negative 1 squared is 1. Negative 2 plus 3 is 1. So it appears the graph is all the way down to negative 5, when x is negative 2. So it goes to negative 5, comes up to negative 1. Since this has a multiplicity that's even, it bounces off 1, comes through the y-axis, crosses through that one, connects up here. Okay, question 5. We have this graph right here, and we have to write the equation in 3 different forms. Standard form, which is also called vertex form, intercept form, or factored form, and the general form, which is probably the one we're most familiar with. But knowing that the vertex is here at the point 4, negative 3 tells us a lot. The vertex is the point 4, negative 3. So that means in standard form we're going to have y equals x minus 4 squared minus 3. What we don't know is what's the value of a, because it appears that this graph is a little bit skinnier than normal, which means that a is not 1. A might be 2, it might be 3. We need to find the value of a. So what you do is you locate another point on the graph that is easy to locate. For example, this point right here. I know for sure that the graph is crossing through the point 3, 0. So that gives me an x value and a y value, which I can plug in for this x and this y right here to help solve for a. So I'm going to let y equal 0. I don't know what a equals, but I'm going to let x equal 3 and solve the equation. 3 minus 4 is negative 1, but negative 1 squared is 1. 1 times a is a, so we have 0 equals a minus 3. If you add 3 to the other side, we get that a is equal to 3. So now we can finish the equation in standard form. Now that we know that a equals 3, there we go. Now we can finish the equation as y equals 3 times the quantity x minus 4 squared minus 3. Now, intercept or factored form, we know that it has zeros at positive 3 and positive 5. Intercept form looks like this: y equals a, and then we have x minus p, x minus q, where p and q would be found from the zeros. So we already know the value of a is 3, and we know that the zeros are 3 and 5, so it's x minus 3 and x minus 5. General form is ax squared plus bx plus c. So you could take either the standard form here or the intercept form here, multiply it all out to get standard form. I'm gonna use this form of it right here, this intercept form, and multiply that together. So we have 3, and then if you multiply x minus 3 times x minus 5, you're gonna get x squared minus 8x plus 15, and when you distribute the 3, you're going to get 3x squared minus 24x plus 45. So that finishes page 2. This question here, question 6, is a lot like the one we just finished. We know that it has a vertex here. So if we're writing the equation y equals a times x minus h squared plus k, these are the values for h and k that we use. It goes in the vertex form or the standard form. So y equals a times x plus 4 squared plus 1. And then they give us another point through which the graph crosses. That gives us another x and a y value we can plug in for this x and this y right here to find the value of a. So y equals negative 1. We don't know a. X is negative 3 plus 4 squared plus 1. Negative 3 plus 4 is 1. 1 squared is 1. 1 times a is a. So negative 1 equals a plus 1. If you subtract 1, you get negative 2. Is equal to a. So the function is y equals negative 2 times x plus 4 squared plus 1. Okay. So we have some kind of a river here. And then looks like this farmer's going to build a rectangular fence on one side of the river. So this side right here doesn't look like it's going to need a fence. So the perimeter that's being used to enclose this is 2,400 feet. Normally the perimeter of a rectangle is 2 lengths plus 2 widths. But since this is only being enclosed on 3 sides, it's 2 lengths plus 1 width. So 2,400, that's the perimeter, equals 2L plus W. Now the problem is saying find the dimensions of the pen that would yield the maximum area. So area is equal to length times width. And the key word here is maximum. Whenever you see this, maximum or minimum, usually that means having a function where we find a minimum or a maximum value on the function. The problem is a equals length times width is not a function. It has one too many variables. We don't know the length, nor do we know the width. So what we need to do is take this equation and solve it for either L or W. What I mean by that is, if I wanted to get W by itself, W equals, you would subtract 2L, and you'd have 2,400 minus 2L. You can take this for W and plug it in right here. So area now equals length times 2400 minus 2L. So now the area is equal to negative 2L squared plus 2400L. This is a function now because it's in terms of only one variable. All we don't know is L. And if you happen to notice here, this is a quadratic function because it's minus 2L squared. Not only that, it's a quadratic function that's facing upside down, like this. So if we can find the vertex, the way that this function is defined, L is the x-axis, the area is the y-axis. So if we can find the vertex, it's going to give us the length that we need, that would give us the maximum area. So rather than completing the square to write this in standard form, I'm going to use the vertex formula. The vertex formula is x equals the opposite of b over 2a. Now in this case, it's not x, it's L. So the opposite of b is negative 2400. 2 times a is 2 times negative 2. So this is negative 2400 divided by negative 4. That's 600 for the length. Okay. Now the width, it says right here, the width is equal to 2400 minus 2L. Well, if L is 600, 2 times L is 1200. 24 minus 1200 is 1200. So the width then must be 1200. And that's what the problem was asking. Find the dimensions of the pen that would yield the maximum area. So these are the dimensions. The length is 600, the width is 1200. It also asks for the maximum area. So if the length is 600 and 600, and then we have 1200 here, then you find the area by multiplying the length times the width. So that's going to give 720,000 square feet as an area. Okay. So the height of the ball after t seconds is modeled by this function. We were lucky we don't have to come up with the function for these types of problems that will be given to us. How many seconds does it take for the ball to reach its maximum height? Again, you need to recognize that this is a quadratic function. It's negative 16t squared. So it's a function, it's a quadratic function that's facing upside down where the x-axis is time, the y-axis is height. So by finding the vertex, we're going to know how long it took to get to the vertex, and we're going to know the maximum height once it gets there. So this is another one of those finding the vertex problems. We're going to use the vertex formula. Vertex is x equals the opposite of b over 2a. In this case, x is t for time. The opposite of b is negative 96. 2 times a is 2 times negative 16, that's negative 32. This equals 3. Since this is a value of time, this is 3 seconds. So it takes 3 seconds to get to its maximum height. What we've got to figure out now is what is the actual maximum height. So you have to plug in a 3. We need to find out the height at 3 seconds. So it's negative 16 times 3 squared plus 96 times 3 plus 64. Okay. Negative 16 times 9 is negative 144. 96 times 3 is 288. This is 144 plus 64, which is a maximum height of 208 feet. Okay, the directions do say use long or synthetic division. Sometimes you do have a choice, sometimes you don't. In this case, what we're dividing by 2x plus 1 really would be better to use long division. Synthetic division would still work because technically it's a degree 1 polynomial, but this leading coefficient of 2 would make that a lot more challenging, so I'm going to use long division here. Recognizing that there's a term missing right here in the middle, there should be an x squared term, so 4x to the third plus 0x squared plus 7x plus 9 needs to be divided by 2x plus 1. Now, we're only focusing on the first term and the first term here. You need to put something up here that's going to turn 2x into 4x cubed, because we're going to have to multiply here. So it turns out this needs to be 2x squared. If you take 2x squared and multiply it by 2x, you're going to end up with 4x cubed. And then if you take 2x squared multiplied by 1, you're going to get 2x squared. When you draw your line, remember to change all the signs. Leading terms cancel. 0 minus 2 is negative 2x squared. And then drop down the terms. Start the process again. What's it going to take to turn 2x into negative 2x squared? That needs a negative x. Negative x times 2x is 2x squared. Negative x times 1 is negative x. Draw the line, switch the signs. Leading terms cancel. We get 8x plus 9. Excuse me. 2x to turn into 8x is going to require plus 4. So 4 times 2x is 8x. 4 times 1 is 4. Draw the line, switch the signs. We're left with a 5 as a remainder. So you add the remainder over the divisor. And that's the answer. This one we absolutely do not have a choice. This has to be done using long division. And again, you need to recognize there's a missing term right here with the x squared used to be. So 3x to the 4th minus 5x to the 3rd, another 0x squared minus 20x minus 5 is divided by x squared plus x plus 3. Now, to turn x squared into 3x to the 4th is going to require 3x squared. 3x squared times x squared is 3x to the 4th. 3x squared times x is 3x to the 3rd, and then 3x squared times 3 is 9x squared. Draw the line, switch all the signs. Leading terms cancel. This makes negative 8x to the 3rd minus 9x squared. Drop down the rest and start again. To turn x squared into negative x, or negative 8x cubed is negative 8x. So make negative 8x cubed minus 8x squared minus 24x. Draw the line, switch signs, leading terms cancel. This is negative x squared plus 4x. Drop down to negative 5. One last time. X squared to turn into negative x squared requires a negative 1. Negative 1 times x squared is negative x squared. Negative 1 times x is negative x, and negative 1 times 3 is negative 3. Draw the line. Remember to switch all the signs. Leading terms cancel. We have 5x minus 2. So you add the remainder of 5x minus 2 over the divisor x squared plus x plus 3. This one we're going to use synthetic division. Finally, we can use synthetic division. Again, because the denominator, or what we're dividing by the divisor, is degree 1 and it has a leading coefficient of 1. And that pesky x squared term is gone again. You got to recognize that. Synthetic division, you just use the coefficients. 1, a 0 where the x squared would be, a 6, and a 5. And then we're going to synthetically divide by the 0 of the denominator, which is 4. Okay, and the algorithm is much different than the algorithm for long division. Okay, this 1 drops down. You multiply numbers on the outside. 1 times 4 is 4. Add the 0 and the 4. 4 times 4 is 16. Add the 6 and the 16 to get 22. 4 times 22 is 88. Add the 88 to the 5 and you get 93. Okay? This is just a representation of the answer. We need to actually state the answer. This is the remainder. These are the coefficients. This is an x squared term. This is an x term. This is a constant. So it's 1x squared plus 4x plus 22 with the remainder of 93 over x minus 4. Okay, another synthetic division. This is just, I guess, more practice. There are no missing terms. So 1, negative 9, 27, negative 27, and we're going to divide by the 0 of the denominator, which is 3. Drop down the 1, add. So we happen to get a remainder of 0. What this proves, actually, this was a later section, but what this proves is x minus 3 is a factor of this large polynomial. So the result, or the quotient, is x squared minus 6x plus 9 with no remainder. Divides evenly. Okay. From section 3.3 in the 6th edition. There was this remainder theorem is what it was called. Rather than taking a -2 and plugging it in for all the x's here, which could be done by hand, it'd be a little harder without a calculator. The remainder theorem says you can synthetically divide, keeping in mind there are a few missing terms here. You can synthetically divide. In the remainder theorem, you actually use the number that's given for the synthetic division. You don't change it. So if you do synthetic division, the numbers get a little larger, but not nearly as large as they would be had you tried to evaluate this just by plugging in the -2. -2 times 34 is -68. -68 times -2 is 136. If you add, you get 137. If you double that, you get -274. If you add, you get -273. So if you evaluate the polynomial p when x equals -2, the result would have been -273. Okay, to show that the 2 really is a 0 of the polynomial, we're going to do another remainder theorem. Okay? So we're going to synthetically divide by 2, evaluate the polynomial here, and we're supposed to show that we get a remainder of 0. That proves that this is a 0. So if you do the algorithm, the result that it's a remainder of 0 proves that 2 is a 0 of the polynomial. Okay, this next section, the next about 5 or 6 problems, all come from either section 3.4 or 3.6 from the 6th edition, or the 5th edition is 4.4 and 4.5. But to find all the zeros, you have to do the P over Q, the rational zeros theorem, and then you have to test some to find out which ones actually work using synthetic division. What we need to do here is the P and the Q, if that sounds familiar. We got to find the P's and Q's and make a list of the possible rational zeros. So P comes from the factors of 12, which are plus or minus 1, plus or minus 2, plus or minus 3, 4, 6, and 12. And then Q comes from the leading coefficient of the polynomial, which in this case the factors are just plus or minus 1. So if we take all the factors of P and divide them by the factors of Q, then really what we end up here is this list. This is a list of possible rational zeros. So what we need to do is go through and you just kind of have to test some to see if they work. You got to leave yourself a little bit of room for these kind of problems, because quite often you choose a couple that don't work before you choose any that do. For example, the most obvious one you would want to choose first is +1. So, we could test 1, see if we get anywhere with it. And it doesn't look like 1 works. So, you go through a couple that don't work until you find one that does. -3 actually works on this one. And I only know that because I have the answer in front of me, so you usually aren't just going to guess right off the bat. So, since we get a remainder of 0, that actually proves 2 different things. It proves that 3 is a 0, or that x plus 3 is a factor. It also gives us another factor right here. That's what synthetic division does. It's pretty useful. We have a factor of x plus 3. We have another factor of x squared minus 4x plus 4. And then we got real lucky in this one, because this quadratic factor factors very nicely into x minus 2 times x minus 2. Usually that doesn't happen. What usually happens is when you get to a quadratic factor, you have to use a quadratic formula. But anyway, the zeros then are x equals -3 and x equals 2, and that one has a multiplicity of 2. Okay, similar thing here on question 16. Got to do the P over Q list and everything else. P are the factors of the constant, plus or minus 1. plus or minus 2. Q again are factors of the leading coefficient, plus or minus 1. So if we take all the factors of P divided by the factors of Q, then this over here becomes our P over Q list. You go through, try some of them work, some of them don't. We get a little lucky in this one because one actually works. So what this proves is that x minus 1 is a factor, and the remaining factor is x to the third plus 3x squared plus 1x minus 2. So we got to continue to do synthetic division because we have to find all 4 zeros. It's a fourth degree polynomial. Right now we only found 1. So go back to the P over Q, try some more, but you don't have to try to do synthetic division anymore on the original polynomial. You need to do synthetic division now on the smaller factor, because any remaining factors of the original polynomial are going to have to be factors of this smaller polynomial. So I'm going to test negative 2 on the smaller polynomial and see what happens there. And it looks like negative 2 is working. So again, we've now found 2 factors, x minus 1, x plus 2, and this factor here is x squared plus x minus 1. Now, this quadratic factor right here does not factor using traditional factoring techniques. We have to factor it using the quadratic formula. So, x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. 1 minus 4 times 1 times negative 1 turns out to be 5. So x equals negative 1 plus or minus the square root of 5 all over 2. So I'm actually going to split this up into 2 different numbers. This is 1/2 plus root of 5 halves, and it's 1/2 minus root of 5 halves. And the reason for doing that is it needs to be written in factored form. So P of x is x minus 1, x plus 2, and now it has 2 other factors that need to come from these zeros right here. So if these are x equals that and x equals that, then this factor is going to be x minus 1/2 minus square root of 5 halves, and we have x minus 1/2 plus the square root of 5 halves. Okay, this one's kind of unusual in the fact that it's actually a little bit easier to find the factors than having to do the synthetic division and all this quadratic formula stuff, because you notice we have a factor of x to the third, a common factor that factors into that. If you factor that out, you're left with x squared plus 9. To find zeros, really what you're doing is solving each factor when it equals 0. So if x to the third equals 0, then x equals 0. If x squared plus 9 equals 0, then x squared equals negative 9. If you square root both sides, you get plus or minus 3i. So then in factored form, it's x to the third times x minus 3i times x plus 3i. And then these would be the zeros right here. Now, you know, you got to think there are supposed to be 5 zeros. This is 2 zeros right here. This appears to only be 1 0, but it comes from the factor x to the third, which has multiplicity 3. So this really counts as 3 zeros, with the other 2 zeros making 5. Okay, question 18. Find all zeros real and complex of the polynomial right factor. This is actually kind of a mean trick. If you did the P and the Q theorem, P over Q, you get plus or minus 1, plus or minus 5, and plus or minus 25. You could test every single one of those and none of them work. Okay? What that means is the zeros of this polynomial are not rational. They're either irrational or imaginary, which are a little bit harder to find sometimes, but this one can be if you think about it as x squared plus 10x squared plus 25, This is a little trick that you would use a lot in a calculus class, but it has some applications to a 1050 class. If we replace the x squareds with a different variable u, for example, then this is nothing more than u squared plus 10u plus 25, which factors into u plus 5 times u plus 5, and then you could just change the variables back to what they originally were. So it factors into x squared plus 5 times x squared plus 5. Again, finding zeros means that each factor has to equal 0. So x squared plus 5 equals 0, and x squared plus 5 equals 0. X squared equals negative 5, so x equals plus or minus I times the square root of 5. And same thing over here, x equals plus or minus I times the square root of 5. So written in factored form, since it's a fourth degree polynomial, we have, really we have 4 factors. If it's all expanded out, we have x minus I root 5, x minus I root 5, x plus I root 5, and x plus I root 5. You could write this a little bit shorter way and square the first. So you could write this as x minus I root 5 squared, and then x plus I root 5 squared. Alright, now we're getting back to the P and Q stuff here on question 19. So the list of P would be the factors of 18 plus or minus 1. There are a whole bunch for 18. 3, 6, 9, and 18. And then the factors of Q over here would be plus or minus 1. So this becomes your P over Q list, because Q is just 1. So going through, finding some that do work, some that don't, just to kind of speed this up here. You'd go through probably positive, negative 1, positive, negative 2. They don't work. You get to negative 3. Finally it does. Negative 1, negative 3, negative 4, negative 12, 6, negative 18. So negative 3 works. So far we have P of x equals the factor of x plus 3 times the factor of x squared plus 4x plus 6. This does not factor other than using the quadratic formula. So x equals the opposite of b, plus or minus b squared, or plus or minus the square root of b squared minus 4 times a times c, all over 2a, so it's negative 4 plus or minus 16 minus 24 is negative 8. And then the square root of negative 8 is plus or minus 2I root 2. So writing this as 2 different numbers, this is negative 4 halves plus 2I root 2 halves, and negative 4 halves minus 2I root 2 halves. And then going even one more step, that would become a negative 2, and the 2's would cancel. So this is negative 2 plus I root 2. Then here this negative 4 over 2 becomes a negative 2, and then that becomes 2I root 2. So the factors are x plus 3, and then x plus 2 minus I root 2, and then x plus 2 plus I root 2. Okay, one more. I know this may be overkill on these types of problems, but they do require a lot of practice to get the method done. So we have a P over Q list of plus or minus 1, plus or minus 3. It looks like negative 1 is going to work. So we have 1, negative 2, negative 2, negative 2, negative 3. And then using this, I'm going to find one more. It looks like 3 works. So I'm going to test 3. So we found 2 zeros, which is giving us 2 factors, plus this is our 3rd factor. So we have P of x equals x plus 1 times x minus 3 times x squared plus 1. This is going to generate two more factors, x squared plus 1. Usually at this point, if you get something that doesn't factor, you would use the quadratic formula. If you have a quadratic factor that's missing the linear term, the term that's usually in the middle, then it's much easier just to set that equal to 0 and solve using square roots. If you subtract 1 and then square root, you get x equals plus or minus I. So then the factors are x plus 1, x minus 3, x minus I, x plus I. Okay, we're just about there. I think this is the last page. Find a third degree polynomial with integer coefficients. So right here, third degree polynomial implies that we're supposed to have 3 zeros, but they've only given us 2. So what you need to read into this problem is they expect you to know the conjugate zeros theorem, which says that complex zeros such as this one, 1 minus I, always come in conjugate pairs. So the other 0 is 1 plus I. So the first step is to write p of x in factored form, x minus 1. The factors come straight from the zeros, and then x minus 1 plus I, and then x minus 1 minus I. Next step is to multiply this all together to end up with an integer coefficient, a polynomial with integer coefficients in general form. So I would multiply these two together first. You're going to get x squared minus x minus ix. I'm just distributing the x's here. Now you distribute the negative 1s. So you're going to get negative x plus 1 minus plus I. And then if you distribute the I, you're going to get plus IX minus I squared. Now, any term that has an I with it here should cancel. We have ix and negative ix, we have positive I, negative I. I squared is really negative 1, so you're subtracting negative 1, which changes into a plus 1. Combining like terms now gives x squared minus 2x plus 2. And that multiplies with x minus 1. So we're going to get x to the third. So you distribute the x here. X to the third minus 2x squared plus 2x, and then you distribute the negative 1. All the terms, and you get negative x squared plus another 2x minus 2. And if you combine all your like terms, you get x to the third minus 4x squared plus 4x minus 2. And there's the polynomial. Actually, that's minus 3x squared from right here. Okay, this is from the very last section in the chapter. In the 6th edition, it's 3.7. In the 5th edition, it's 4.6. The directions are very detailed in that they give you most of the steps you need to take to graph a rational function. You can find intercepts, the asymptotes. I'm actually going to start with the asymptotes and then do the intercepts second. So the vertical asymptotes are the domain restrictions. X cannot be 1, so there's a vertical asymptote right there, x equals 1. X cannot be negative 3, so there's another one, x equals negative 3. Okay. Now the horizontal asymptote is found by comparing the degree of the numerator, which is degree 1, to the degree of the denominator, which is a little hidden. If you multiply this all out, you'd have a degree 2. So the numerator is smaller degree than the denominator. That means that the horizontal asymptote is the line y equals 0, right along the y-axis. Now the y-intercept is found by letting x equal 0. So if you plug in a 0 for all of these x's, you're going to have 2 over negative 3, it looks like. Negative 2/3 is right about there, so 0, negative 2/3. And then the x-intercept, or intercepts, if there are several, would be found by solving the equation in the numerator. In this case, x plus 2 equals 0. So the x-intercept is negative 2. Okay, now these vertical asymptotes mean that when a graph approaches a vertical, when a rational function rather approaches a vertical asymptote, it either approaches positive infinity or it approaches negative infinity. But it doesn't just stop and pick up somewhere else. That would be a piecewise function. So over here to the right side, for example, the behavior of these graphs is always very, very similar. Either the graph has a piece up here in this corner or it has a piece down here in this corner. It's not going to have both because it wouldn't be a function, it wouldn't pass a vertical line test. So we got to figure out, is the piece down here or is it up here? So the way that we can tell is by, let me fix this here. I'm going to just plot a point and let x equal 2 for that. So if x equals 2, we change all the x's to 2, we get 4 over 2 minus 1 is 1 times 5, so we get 4/5. So 2 comma 4/5 is right about here. Now that one point is sufficient to determine that the entire portion on this side is above the x-axis. Okay. The reason I know, or that we can claim here that the entire portion here is above the x-axis, if one point is above, and then all of a sudden some points are below, that would mean at some point the graph would have to cross through the x-axis somewhere here, and there isn't an x-intercept to allow the graph to do that. So if one point is above, at least on this side of that vertical asymptote, all the points are above. Using a similar type of argument over here to the left, if we tested -4, for example, with all the x's, then we get -2, -4 minus 1 is -5 times -1. So we're at -2/5, which is right about here. In a similar argument, if one point is below down there, all of them have to be, they all have to stay below because it can't cross up above the x-axis. There aren't any x-intercepts here to allow it to do that. Okay. Now we have an x-intercept here and a y-intercept here. The graph has to be at least connected between those 2 points. We got to figure out what happens after. So for example, after the graph passes through the y-axis, it's approaching this vertical asymptote, so it has 2 options. It can either turn up and go up to infinity, or it crosses through and goes down towards negative infinity. Now, if we're saying that it's going to go through, cross up, and go up to infinity, that means it would have to cross through the x-axis right here. It can't do that because there's no x-intercept right here, so it has to turn down and head toward negative infinity. Now here the graph crosses through the x-axis, and it has the same 2 options. Either it goes up to infinity or it goes down to negative infinity, but it's already above the x-axis. It can't turn down and go below it again because there's no x-intercept here. So this piece of the graph goes up to positive infinity. Okay, 23, last one. It's going to be much easier to consider this in factored form, x minus 3 times x plus 3, and then the denominator is x plus 4 times x minus 2. So, same steps. The vertical asymptotes are the domain restrictions in the denominator, so we have one at x equals -4 and x equals 2. Now the horizontal asymptote is found by comparing the degrees. Since these have the same degree, that's the case where you have to divide the leading coefficients. 1 divided by 1 is 1, so the horizontal asymptote is y equals 1. Okay, now the y-intercept is found by letting x is equal 0. I'm actually going to revert back to the unfactored form. If all of these x's are zeros, then those all disappear. We get positive 9/8. So it's 0, 9/8. Now 9/8 is just slightly larger than 1, so it's right here. The x-intercepts are found by solving the equation in the numerator equal to 0. That's going to give us 3, 0 and -3, 0. And this one's going to be a little bit quicker to determine where the graph is because the horizontal asymptote is not on the x-axis. For example, right here, this one point is below the horizontal asymptote, so we know that this whole piece of the graph is going to be below. And then similarly, we can argue that over here on the left side, since there is no x-intercept anywhere over here on the left side of this vertical asymptote, the graph cannot be contained in this bottom corner because it would have to cross the x-axis at some point. So it's a safe conclusion that this piece of the graph is in the top left corner. Okay. And here we know that at least the x and y intercepts have to be connected. Right? As it passes through the y-axis, it's going to continue to move up towards positive infinity. It can't pass through the y-axis and turn down because it would have to cross through the x-axis again here somewhere, which it can. And then here it crosses through, and it has to stay underneath the x-axis now. It can't turn back up and come back up here because it would there'd have to be another 0 here to allow it to do that. So that graph would look something like that.